class. Today we're going to be talking on the applications of clocks D flip-flop. So one of them is detecting input sequence. So let's say you have your input D like this, and then you have your clock signal going like this, and this is a PGT. So now the output Q will be according to the truth table, it is 1 at the PGT, Q will be 1. It is 0, the PGT, Q will also be 0. So we're going to assuming Q initial is 0. Now we've gotten to the clock signal. We're going to go what is D at this point? D is 1. So Q is going to become 1. Now what does this have to do with input sequencing? Let's replace D with A and the clock signal with B. Now a person working with signals to be able to tell that input A, that is what's here, went up before input B because of the way the Q signal came out. That is what input sequencing means. Now if we try to take up B, I'm using A and B in this case again. Let me space it out so that I won't get confused. If A came up and then B, which is the clock signal, came up before A, and down here, and up here. Now let's see how our Q output will look. You see our Q initial is 0. When it gets to the PGT, it's going to copy what it sees at A. A is 0. So it's going to copy what it sees at A till it reaches the next NGT. At this point, you can see that A is 1. So Q will become 1. Now, a person working on this signal will be able to know that, okay, B came up before, made a step up before A because of the way their output Q looks like. So that's just what detecting input sequence with the clock D flip-flop means. So the next application about the clocked D flip-flop is detecting a transitional event. So as you can see here, let me zoom in. This is a XOR gate. A XOR gate checks whether two inputs are different. So if you have 1 and 0, these two inputs are different. So the output edge will be 1. Sorry, edge. If you have two inputs that are the same, the output will be 0. That's how a XOR gate works. So now in this case, what's this used for in this particular circuit? If the input signal is 1 and the output is 0, that means initially, or rather let me explain it better, the input signal came in as 0 and D was also 0. Now the input signal has changed to 1. The XOR gate is going to check whether the input signal and D are still the same. If they are no longer the same, it will know that, okay, the input signal has changed. That is this transition detection. Now let's look at it in output waveforms. So we have our input signal and our output Q. So now we need to draw our edge signal. So at every point we see a change in the input, we're going to draw a line, and on our Q, there's another change here in our input signal. We can see another change here in our Q. Now our edge signal is going to check whether anything is changing at this point. So edge at first is input is 0, Q is 0. Since they're the same, edge is going to be 0 as well. Next, here we have at this point between here and here, we have that input signal is 1 and output is 0. That means they are different. So, and when they are different, edge is going to be 1. So edge is going to come up here by 1. Next, at this point, see that input signal is 1 and Q as output signal is 1 as well. These are same same input, which will result in a 0 at the edge because this is a XOR gate, an exclusive OR gate. So it's going to drop down, edge is going to drop down to 0 till it reaches the next change. At this next change, what do we see? Input signal is 0, Q is 1. They are different, 0 and 1. So edge is going to output 1. Next, we have here that input signal is 0 and Q is 0. These are same signals, 0 and 0. Edge is going to output 0. And that's just what we have for the output waveform. So at this point where it's going off, so an individual will be able to know that okay, there's a change in the input signal and it's in the most recent input signal and its former output Q. So that is the application of the flip-flop here. Now for the next one, we have that it is used for the clock D flip-flop is used for parallel data transfer. So this is a parallel data transfer structure. So this is our source register, that is where where the information is coming from, and this is the destination register where we want to store the information in. So if taking for example at the source register we have 101 and we want to store it in our destination register, how are we going to do this? Using this D clocked flip-flop at this is a PGT clocked D flip-flop. So at the rising transition, every information here is going to be transferred to this point. So let's see how that is going to work now. So at the PGT of the clock signal, 1 is going to come here, 0 is going to come here, and 1 is going to come to Y naught. Please note that just because the information has transferred, it does not mean the x1 and x0 have cleared. They have not cleared at all. Rather, they have only just made copies of themselves to Y naught. So that's how parallel data transfer works. And you notice that the information transfers at once. So it doesn't actually transfer as 1, then 0, then 1. It actually just transfers at once. This 101 here just gets transferred immediately to here as 101 at once. That's the good thing about parallel data transfer. The information is transferred at once. Now let's look at the serial data transfer, another application of the clocked D flip-flop. So this is the application in serial data transfer. So this we are still using the clocked D flip-flop. So let's say this is the source register, this is the destination register. Now let's say the information we want to pass on to the destination register is 1, 0. So the difference between serial and data register is that the serial data moves the bits one by one. So on the first clock pulse, we're going to have here is 101. It's going to move to the right by just one step. So we're going to have 0, 1, 0, 1. You can see 101 has moved a bit. You can see it on the table here. 101 has shifted by 1 bit. Now next, when the clock pulses again upwards, when it pulses upwards again, it's going to shift. So we're now going to have 0, 0, 1, 0, 1. You can see 101 has shifted. And now we're at Y2 and Y1. Now you can see that on the table here. You can see we have shifted now. Now next, when we have another pulse, the data is going to shift again, meaning we have 0, 0, 0, 1, 0, 1. Now we have successfully moved all the information we want to the destination register. So I wanted to take some key notices between the parallel data transfer and the serial data transfer. For the parallel, the information is transferred at once, but for the serial, data is transferred simultaneously at each clock pulse. For the parallel data transfer, the information at X is not cleared, but for serial data transfer, as you can see here, X1, X2, and X0 have become 000, which means the original data that were at the source register have cleared and been moved to the destination register. So these are the two key differences between the serial data transfer and parallel data transfer, and both can be done using the clock.